Hello there. In this video, I want to find the equation of motion for a spherical pendulum using Lagrangian mechanics. At the time that I'm posting this video, this channel just reached 100 subscribers. So thank you very much to everyone that's subscribed so far to this channel. So yeah, let's just keep going. Let's make sure to have extra fun in this video. You know, physics is always fun. But, this is a big milestone, triple digits. So let's get to this problem. Alright, so the spherical pendulum is just like the simple pendulum in its setup, right? We have this mass m here attached to some massless rod of length L. It's in gravity, so then when we're going to let it go, it's going to start swinging back and forth. The difference here between the simple pendulum and the spherical pendulum is we've gotten rid of the restriction that this mass must be in 2 dimensions. Now this mass can move around in all 3 dimensions. So the first question we need to ask is how many coordinates do we need to represent the motion of this pendulum here, right? And so we always start by figuring out the degrees of freedom of our system. Okay, so the degrees of freedom are equal to 3n minus c, where c is the number of constraints in the problem. How many constraints do we have? Well, we just have one constraint here. This rod is at some fixed length L. And of course we have one particle, so 3 minus 1 is just equal to 2. So we have 2 degrees of freedom for this system. That means we need 2 independent coordinates in order to describe the motion of this pendulum. Right, and let's make this connection now. Since we have 2 independent coordinates, we should be getting 2 Euler-Lagrange equations. We're going to have to write 2 of these guys out, because you write one Euler-Lagrange equation for each coordinate that you're interested in. So now we have to decide what are these coordinates going to be. And of course, as the name implies, that we have a spherical pendulum, let's go ahead and use spherical coordinates for this, right? So if I can go ahead and define, I'm going to define my polar axis downwards here. And I'll just go ahead and call this z-axis. And just so we have these other reference axes, I'll go ahead and call this x and y here. Okay. And if we do that, we can go ahead and define a polar angle here. So let's go ahead and say that my mass, I'm going to draw these blue lines to kind of project the location of my mass, just like this, okay? And of course I'm going to have some polar angle, theta, that this mass makes with my z-axis here. And let me move this x-axis down, I'm just projecting it down here, just like this. And so then here we can see that I have this azimuthal angle phi here that this mass makes with my x-axis. Of course, also in spherical coordinates, we should track the radial distance of the mass away from the origin. But of course, this radial distance is just going to be equal to the length of the rod at all times. That's our constraint, right? So this fact that r is equal to L, we don't need to track the radial distance. We already know what it is at all times. So we only need these 2 independent coordinates, theta and phi, in order to know everything about the mass's location. Alright, so we've got our coordinates. We don't need this degrees of freedom anymore. We know that our number of chosen coordinates matches up with our degrees of freedom. Perfect. So in order to find our equations of motion, we need to define our Lagrangian first, as always, right? Our kinetic energy minus our potential energy as a function of these coordinates. So let's go ahead and start by finding the kinetic energy of our particle. So we know that very generally, kinetic energy T is equal to 1/2 times the mass of my little bob here, times its velocity squared, which I'm going to write as the magnitude of its velocity, just like this, squared. And we also know that we can rewrite this as just m over 2 times r dot dotted with itself, just like this. Taking the dot product of our velocity with itself is effectively squaring the speed that's doing the same thing. Okay, so let's go ahead and recognize this. So what's kind of our key set of steps here? Well, what I can do is I can write out the position of my particle as a function of these coordinates. Then we're going to take the time derivative of that, okay? And then we're just going to plug it into this equation here, and we're going to get out our kinetic energy. And so let me just start by writing out that our position is going to be equal to some component in the x hat direction plus some component in the y hat direction plus some component in the z hat direction. We're going to find each of those, components in each of the directions in terms of these spherical coordinates here, and then taking the dot product is going to be really, really simple. Okay, so let's go ahead and start breaking down this set of triangles that we have here. So we know that this length here, this is going to be L times sine theta. We know that this height here is going to be L cosine theta. Okay, and let me go ahead and break this bottom triangle here as well. We're going to break it into the component that's going in the x direction. Okay, so something like this, along with some component that's going in the y direction, something like this. Okay, and so if we recognize that, then if this hypotenuse is L sine theta here, then this distance here is going to be L sine theta cosine phi, and this component down here is going to be L sine theta sine phi. Do you see that very clearly? I just broke these two triangles down to come up with our components. Okay, and so let me just make this connection here. So this is our equal to A, this is our x hat component. This is equal to B, this is our y hat component. And this is going to be equal to C, this is our z hat component. Okay, so let's go ahead and write all of this down. So we have that our position is going to be L sine theta cosine phi in the x hat direction plus L sine theta sine phi in the y hat direction plus L cosine theta in the z hat direction. Beautiful. Okay. So from here, this just tells us the position of our particle, right? And remember, these theta and these phi's, these are going to be changing with time. So these are both, they're functions of time, okay? So what we need to do from here, and I'm going to return back to black now that we've, figured this problem out. Let's go ahead and figure out this next problem. What is the velocity of my particle as a function of time, right? So this is going to be equal to, I have to take the time derivative of this entire thing, right? And so what's that going to involve? That's going to involve a bunch of product rules, right? Because I have this theta of t, I have this phi of t in here, right? And then likewise there and in here. So I'm going to have to do the product rule a little bit. That's okay. Let's go ahead and do that. So let's go ahead and start by taking the derivative of this first term. I'm going to have L. Let's go ahead and first differentiate the theta part, okay? So I'm going to have theta dot, pull that to the outside, cosine of theta times cosine of phi. Okay, plus, now let's differentiate the phi part, leaving the theta part constant. And so we're going to have L times phi dot sine theta times a minus sine phi. So I'm going to go ahead and I'm going to swap out this little plus sign to a minus sign. And this is going to be acting in the x hat direction. Okay, great. Let's go ahead and take our time derivative of this y hat component now. So next we're going to go ahead and get L times theta dot cosine theta sine phi. Okay, and now this is going to be plus, let's go ahead and focus on this phi part here, L phi dot sine theta, oh whoops, I forgot to differentiate, here we go, cosine phi in the y hat direction. Beautiful. And next we're going to have this last term here, which is going to be the easiest of the three, so we're just going to get minus L theta dot sine theta in the z hat direction. So all that we've done, we just took the time derivative of our position vector. great, and we're left with this. Okay, so this might look a little bit gross right now, but we'll see that it reduces down when we go and, plug it into this equation for t here. So let's go ahead and start just by taking the dot product of this velocity with itself, okay? So we're going to start by doing r dot dot r dot. So I'm going to go ahead and do a little magic trick with editing here. And there we go. With this little magic trick, now all I have to do is square each of my components and add them together, which is what I just went ahead and wrote out here. So now we just need to go ahead and square each of these out. Okay, and I'm going to go ahead and do another little magic trick, and I'm going to go ahead and write all of this out. Alright, so with that little magic trick, I went ahead and just expanded this whole thing out, just applied these squares, and oh my goodness, it looks like we're left with a lot of mess here. But wait, this isn't that bad, because look, first off, we can just cancel this guy out with this guy. Okay, let's go ahead and use some trig identities. Those are our friends. So, first off, we know that cos squared of an angle plus sine squared of an angle is just equal to 1. So let's go ahead and match up some terms here. Okay, I see this and this here. Cool. I see this and this here, right? These both have the same start. This has the same start here. Cool. So now if we go and we add all of this together, right, we're going to be left with L squared. I'm going to pull the L squared out as well. We're going to have theta dot squared cos squared theta plus phi dot squared sine squared theta plus a theta dot squared sine squared theta. And oh my goodness, look at this again. We can match this and this. They both have the same coefficients, theta dot squared. Okay, great. Let's go ahead and put this together. We're going to have equals L squared times theta dot squared plus phi dot squared sine squared theta. And so with this, we can now plug this, right? We can plug this guy here, I know I'm zooming out a lot, all the way back in for r dot r. So our kinetic energy is ultimately going to be equal to, T is going to be equal to m over 2 times L squared times theta dot squared plus phi dot squared sine squared theta. Alright, one step down. Next, we need our potential energy as a function of these coordinates. Okay, this is going to be a lot faster, right? And this time what I want to put our focus on is that our pendulum has an equilibrium position here, right? When it's not displaced at all, it's just pointing straight down. And I'm going to go ahead and define this spot here as my location where my potential energy is equal to 0, okay? If I do that, then we can see that if this mass here is at some height h, then my gravitational potential energy is just going to be equal to mgh. So we just need to find h, right? And oh my goodness, this is actually pretty easy, because if this entire length here, right, straight down, our equilibrium position here, sorry, this line is not very straight, let me just use a straight line tool. We're just going to go straight down like this, right? If this length here we know is just L, the length of our rod, right? Really what I need to do is I need to find this height here, take this here, subtract this, and that's going to give me my height h. Do you see that? Right? And so, oh wait, we already have that component. Oh my goodness, this is so easy. We already have this height here. So we just take, this is going to be equal to mg times L minus L cosine theta, or mgl times 1 minus cosine theta. And that's our gravitational potential energy. And so, after we found our kinetic and potential energy, I just plugged them in. And now we have our Lagrangian. All of that work paid off to make this beautiful gem here. And with this Lagrangian, we're going to be able to get the equations of motion for this pendulum. So remember, we need to make two Euler-Lagrange equations. One for my first coordinate theta, right? That would correspond to setting j equal to 1, calling this q1. And then we need to make an Euler-Lagrange equation for phi, right? That's going to be my second coordinate, q2. So we need two Euler-Lagrange equations. So let's go ahead and start with our equation for theta, okay? And so I need to collect some derivatives here. I need to collect this derivative, and you know, we'll go from there. So let's go ahead and start by finding dl with respect to theta dot, okay? And you know, we can see that this is not bad at all. I only have theta dot actually appearing one time in this entire equation here. So I'm going to be left with ml squared theta dot when I take that derivative. Okay, cool. And we know we don't just need the derivative with respect to theta dot. Then we have to take the time derivative of that after. So let's go ahead and next go ahead and take our time derivative, d dt, and we're going to be left with ml squared theta double dot. Cool. Next, let's go ahead and collect our dl with respect to just theta. Okay, so we need dl with respect to theta. And this is going to be equal to, okay, we have a couple of theta terms here, so let's go ahead and be careful about this. We're going to have ml squared, I'll go ahead and pull this phi dot squared out, times the derivative of sine squared theta. We're just going to use our chain rule, and we're going to get 2 cosine theta times sine theta. Okay, and now we just have to do it for this term here. So that's going to give us minus mgl sine theta. Okay, and now, just like in our Euler-Lagrange equation, we just have to take the difference of these terms. All right, and so after taking the difference of those terms, and of course setting it all equal to 0, just like we had in our Euler-Lagrange equation, I get my equation of motion just like this. I also did a little bit of rearrangement by isolating theta double dot here. I divided my masses out and I divided by L squared to isolate this guy. So we just have this really nice, elegant form here. I also did catch, I had a little error. I had a little 2 factor on, you know, this term here. So that shouldn't be there. I went ahead and fixed that up. But let's go ahead and just take a second to appreciate this this equation of motion, right? We should be able to extract the equation of motion for a simple pendulum from this, right? So for example, if my angle phi here, let's go ahead and say that my azimuthal angle is fixed, right? I put that constraint on here. Then this should just return me the equation of motion for a simple pendulum. Now this guy is just constrained, this is fixed, so it just swings back and forth, only theta can change. Okay, and yeah, that's exactly what we have here, right? If phi is fixed, then phi dot must be 0, this term must 0 out, and I'm going to be left with the equation of motion for a simple pendulum. Right, so now that we have this equation, let's go ahead and take some time and get the equation of motion for phi. Okay, so next let's go ahead and get our equation of motion for phi. So first thing we need, just like before, dl with respect to phi dot. Okay, what's this going to be equal to? All right, so we just have one term with phi dot here. So when we take this derivative, we're going to have ml squared times phi dot times sine theta. Oop, this should be sine squared theta. There we go. And now I'm going to hold off on taking the time derivative of this, and we'll go ahead and see why in a second. Okay. So next, if I take dl, and I'm going to just take this derivative with respect to phi next, right? That's the second coordinate we need. Okay. There's no phi that shows up in this equation. Isn't that interesting? So this derivative just equals 0. So now, okay, I'm not going to take the time derivative of this first guy explicitly. So I'm going to leave d dt of ml squared phi dot sine squared theta. Okay, and now we're going to plug our terms in to the Euler-Lagrange equation, and we're going to be left with d dt times ml squared phi dot sine squared theta. This is equal to 0. Or in other words, if the time derivative of this quantity here, is 0, then this quantity itself, ml squared phi dot sine squared theta, is equal to a constant. Okay? And what's really interesting, and go ahead and take a second and verify this for yourself, this is the z component of my system's angular momentum. So actually what we ended up verifying by creating our equation of motion for phi is that the z component of my system's angular momentum is conserved. So that's really powerful. So that's why I didn't go and take this derivative with respect to time. So we find that Lz equals constant. We found a conservation law. And that just goes to show another big power of these Euler-Lagrange equations, that when you get zeroing out terms, right, you can end up finding conservation laws very quickly with the Euler-Lagrange equations. All right, and with that, we found the equations of motion for our spherical pendulum. I hope you found this video helpful. If you did, consider subscribing to the channel. I'd really appreciate it. But other than that, thank you so much for watching.